Thank you so much for joining another episode of SunEarth webinars. Today, I'm joined here with Chief Technician Bob Danielson. We're just going to give it a few minutes, wait for other guests to join us. Everybody's running a few minutes late, and then as soon as probably in about a minute or two, we're going to get started on today's webinar. Alrighty. Okay, so without further ado, I'm going to get started on our presentation for today. Today we're going to talk about solar water heating and combining that technology with geothermal heat pump technology. In our previous webinar, we did talk about combining solar water heating with air source heat pump and basically continuing the same theme of combining different technology to address different heat loads. Today we're going to look at geothermal heat pumps and solar water heating. So today's presented agenda, we're going to look at a little bit of information from our previous webinar, some of the important stuff that we went over, some of the market trends that we're seeing, some of the motivation behind combining these high efficiency technologies, these green technologies. We're going to talk about solar water heating systems, how they work, the components, and different types of solar water heating systems that exist. We're going to briefly review the ground source heat pump technology, how it operates, how it works. We're going to talk about the benefits, definitely, how these two systems are combined and why would you combine them, basically. There are a couple of possible configurations for these systems that we're going to review. We're going to look at some case studies for both geothermal and then combining solar thermal and geothermal in large-scale district heating applications. And then at the very end, we're going to have a Q&A to go over any questions that you guys might have. So quickly, some of the main topics, some of the main stuff that everybody's talking about nowadays, especially in the energy circles, is decarbonization, electrification. So the meaning of decarbonization, pretty straightforward, is basically eliminating the release of carbon gases into the atmosphere, or basically somehow eliminating them while they are there, kind of absorbing them and getting rid of them. So that's part of the effort, and as part of that effort, a lot of traditional heating solution, mostly based on fossil fuels, are now being replaced with alternative renewable technology that can basically deliver the same heat and not have the same environmental impact. So when people started looking into this, one of the solutions definitely, or a step toward that, is electrification, using electricity instead of fossil fuel locally. So that's when people basically realize the enormous heating load that we're dealing with. Basically, when we look at this across different industry, across different sectors of industry, that how much heating is required from industrial process heat all the way to residential domestic water heating. There is an enormous heating load that we need to address, and that changes from different areas. For example, in the high Sierra mountainous area, 30% to 40% of residential carbon footprint is from domestic water heating and space heating applications. That's where we see a lot of basically fossil fuel being used, and as a result, a lot of carbon being released. But then if that is being replaced by electricity, how are we going to do that? How are we going to do that efficiently? One thing that we have to realize is electrification is not synonymous with decarbonization. If your electrical grid is not renewable, using electricity locally only means you're basically using fossil fuel somewhere else and then adding both the energy cost and the monetary cost of transferring that energy from that plant that was generating electricity from fossil fuels to the place of consumption. So not only it could, actually it's not going to save any energy in the large picture, it's actually going to have a larger environmental impact once we start really looking at it. So again, this heating load, this elephant in the room that nobody was thinking about, is now something that we're seeing that 30% is a huge load, and if you can offset that by any means, will have a significant impact. So there's a lot of national trends here in the US, and we see this globally, but we're more focused here on our country here, what's happening here. We see a lot of different cities, jurisdictions, states adopting net zero or basically zero carbon measures by different years. They are areas that are really going hard. They want to reduce by 20%, 30% in the next 5 years or so. And then there are 20 to 60% reduction within the next 10, 15 years. Different goals, different areas, and we will see more and more of this trend. And these will be partially due to the environmental concerns that we have, stuff that you're seeing that's happening right now. And then another impact will be basically the need for energy independence. So we have to realize we are seeing this fluctuation in international cost of especially fossil fuel, and how different trends in the world can impact that. And then we see that with local generation of renewable energy, you have an upfront cost, but then you have that energy independence because you're not relying on another country, so to speak, to provide you with your energy. You're generating what you need locally. Once we start looking into the water heating technology, and Bob, you know this very well, solar thermal can pretty much pair up with any water heating or heating technology for that matter. Basically working as a preheating, parallel heating, depending on the design of the system, but pretty much solar thermal can branch into all types of heating, on-demand, storage, traditional oil and gas fired, all the way to heat pumps. And it's just realizing that solar thermal, by definition and by nature, is a very high efficiency system with a very high coefficient of performance, because especially with the flat plate collector systems, we're looking at a very simple system that generates a lot of energy and uses a very little amount of energy to generate that energy, basically observing the sun energy and turning it into heat energy. So with that also comes a requirement, and that's the requirement for some sort of a backup, because hot water, of course, is a luxury, but then a lot of hot water, or what you need, is a necessity. The minimum is the necessity, right? Yeah. A lot of it is a luxury. The minimum required that you need for your day-to-day living is an absolute necessity. So you have to be able to provide hot water year-round, or there are areas that you need to provide heat, for instance, for the majority of the year, or a good part of the year, anything. Basically, so in order to be able to do that and use solar thermal with that, we have to create we have to design some sort of a backup, basically. So if there is going to be a backup, and so we know solar thermal is this system with great potential, good efficiency, high COP. And if you're moving toward that decarbonization, if you're moving toward that electrification, doesn't it make sense to just pair it up with the most efficient backup of system that we can find out? So once we look at those, heat pumps have great COP, they are very efficient, and pairing up with solar thermal, they can create this system with a very high average COP that can now provide heat year-round without interruption, because if there is a period of time, for example, a week of clouds and rains and stuff, you still have your heat pump to provide the heat that you need, and then solar thermal will take care of the rest. So that's why we see these designs going, and then once we look at it in this chart, we kind of see the best technology, so to speak, for solar thermal to pair up with, as far as in electrical technology, is the heat pump. So both the solar, basically ground source, and the air source heat pump, liquid source and air source heat pumps are great candidates. So let's talk a little about solar water heating. You know, we're talking about this systems being quite simple, very high efficiency, and here we kind of can see why. So we have systems here that basically, in order of efficiency, for solar thermal, the thermal siphon system is very simple. Basically, you have a collector, you have a storage tank placed higher than the collector itself. The heat generated by the solar energy causes the natural thermosiphon movement of the water in the system, sending the hot water to the storage tank and pushing the cold water down to the collector. And by repeating that cycle, you eventually heat that tank. Some of these have backup system on it. Most of the time, this thermosiphon system, we see them on residential application. Sometimes they can potentially be banked together for larger applications. Then it's an ICS system. Basically, ICS refers to integrated collector and storage. So basically, the function of collecting the solar energy is combined with the function of storing the solar energy. So these are the units that have the storage capacity built into the collector themselves, and because there is no internal backup, they're usually paired up with an external backup, either on demand or a storage type of a backup. Again, we see most of ICS systems on residential applications, but potentially they can be used in some commercial applications. And now we move on to the realms that basically for active systems, we see these in very basically from single collector, single tank system for residential, all the way to thousands of collectors for very large tanks for district heating and applications like that. And that's the interesting part, and that speaks to the simplicity of these systems, because essentially everything remains pretty much the same. All the components remain the same. It's just the size of the components and the quantity of the components change. But you always have a collector. In an active indirect drainback system, you have a drainback vessel that is used to protect the system against both extreme ends of temperature range, basically both stagnation, overheat temperature, and freezing temperature. There's a heat exchanger, either internal or external, into the storage tank, and solar energy is transferred through that heat exchanger to your solar storage tank. So again, in these systems, the components remain the same. So on a commercial system, you might have tens of collectors, hundreds of collectors. On a larger drainback system, on a larger heat exchanger, providing heat to a multifamily building or a commercial application. Right. Moving on to the next one, we have active indirect glycol system. Again, in this type of system, the freeze protection method is using a mixture of water and glycol, hence the indirect glycol name, as your heat transfer fluid. There's an expansion tank to protect the system against stagnation overheat situations. So again, the heat transfer fluid is pumped through the collector, gathering the solar energy, transferring it to your storage tank through a heat exchanger. And same principle applies. Same components, just larger and higher quantities. And then we have the most active direct system. And in active direct system, you just basically eliminate the heat exchanger. The fluid in your tank is the same fluid as your heat transfer fluid, basically. And the efficiency here is really dictated by the flow rate of the system. That's one of the main reasons why, and that's why we see higher efficiencies in active systems compared to passive systems such as thermosiphon. So these 5 types of system pretty much cover the majority, right, Bob? The majority of
yeah, most systems are, most of the ones that would be paired with a ground source geothermal system would be the active systems, whether drain back or indirect. Though generally, because we're talking cooler climates and freezes, we're going to there would be a focus on indirect drain back and indirect glycol systems.
And sometimes, I mean, now that you're pointing that out, I've seen in active indirect glycol system, the heat transfer fluid that is used in the geothermal loop is the same heat transfer fluid that is used in the solar loop. So they kind of can run these interchangeably, and we'll talk about the possibilities and the benefits of being able to do that, kind of running your geothermal loop either directly or indirectly through your solar loop. So yeah, thank you for pointing that out. Thank you, Bob. Yeah, so those active systems, those 3 basically are the ones that we'll see paired up. The indirect ones, right?
The indirect, yeah.
The 2.
Active,
indirect, drain back.
There's no freeze issues with those generally, and if there's no freeze issues, then the climate is such that your heating load may be very low. So, put on a sweater in those climates. You won't see generally a geothermal ground source heat pump system there generally.
Basically, preparing for this presentation was a learning experience for both of us, I think, Bob, because when it comes to solar thermal, we know, I think, a sufficient amount of information, and we have a good amount of knowledge and experience in solar thermal manufacturing, deployment of the system, and all that. But obviously, geothermal is not something that we've ever manufactured or very involved with the manufacturing. It's just the fact that we know these systems pair up very well, and all the empirical evidence and all the research data suggests that these are great technologies to combine. And there are tons of case studies, especially in areas such as for example, colder climates in Europe, where energy is expensive and the need for higher efficiency systems was a reality a long time ago. We see a lot of systems that are working, and they're working very well. So once we started looking at these systems, again, we realized there are so many different types, so many different ways that these systems work and operate. So we're going to try to keep it to a very simple level, to our level of understanding of geothermal technology. But one thing that Bob taught me was the difference between geothermal and the geothermal heat pump. So when we talk about geothermal technology per se itself, is usually using deeper boreholes, deeper trenching, and taking advantage of the Earth's heat itself coming from Earth's core. Once we look at geothermal heat pumps, on the other hand, we are looking at lower depth of
frost line.
Exactly, below frost line.
Depending on where you are, 6 feet. A lot of the Midwest, Ohio, Illinois, Indiana, a lot of heat pump systems there, and they're not terribly deep in the ground, just below frost line. You get up high, up in Dakotas and Minnesota, Wisconsin, they may be a little deeper just to have heat when they need it, which is then down in the ground, because it does freeze frost lines in anywhere from 4 to 8 feet that they have to consider when they do these systems. That's local, so you just, most people that are doing them know the depth that they need to bury their field loop fields in.
Exactly, and again, so there is a temperature range that most of the, that depth of the ground will stay within year round, but then we are also seeing changes in that with the changes in climate, with the changes of environmental temperature. And we're going to look into what happens when we combine these two technologies with one another. So this is something that I spoke about briefly at the beginning, and it's the coefficient of performance for the system. As I mentioned, solar thermal, using a relatively speaking low energy consuming circulating pump to transfer a large amount of solar energy from the collector to solar storage tank in the form of thermal energy. Once we look at the energy generated by the system compared to the energy consumed by the system, we usually see COPs anywhere between high teens to mid 20s. This is generally speaking. Technically speaking, once you look at any passive system like a thermosiphon system or an ICS system, you have zero energy consumed by the system. There are no pumps, no moving parts, nothing. And there is a lot of energy being produced by the system. So if you look at that, technically any number divided by zero is infinity. So you have a COP of infinity. But we don't want to get into those technical discussions. On active systems, when we really look at the performance of a system after 4,000, 6,000 hours of operation, you see our COP of average 2022 for a commercial size solar water heating system, especially if the system is sized right, if the pump is sized right, and if the system is designed and deployed by a solar expert who really knows what they're doing. You will even see higher COPs, even higher than that. So in any case, once we combine that with, as I mentioned, we need some sort of a backup for our solar water heating system. So we'll look at the other high COP options available on the market, and a geothermal system is a great candidate because you have a COP of on average 3.5 to 4. And once you combine these two systems together, you get a system that gives you a total average of about 10 to 12 year round. So basically, if you just put a heat pump, for every 1 unit of energy that you put in, you get, let's say, 3.5 back. If you put a solar thermal system, you will get 20 back, but you might not get that 20 back all the time, depending on solar availability. But once you combine these two systems, you can now have a system that you get 10 to 12 units back for every unit that you put in, and you have that year round. Another thing that we see, especially when you're talking about space heating, Bob, we run to this problem like quite a lot because space heating is seasonal, right? If you need heating, let's say 4 months a year, 5 months a year, you don't need it year round. But when we design a solar thermal system to cover a large portion of the space heating for any type of application, commercial or residential, we have to be careful of what to do with that heat energy during summer. So there are different things that can be done. There are absorption chillers, for example, that can be adopted to generate cold during the hot time of the year or summertime of the year. Or if you know that you're in an area that doesn't have summers that need so much cooling, but you have harsh winters, maybe there's another application. You can put that heat from those collectors. You can use your underground borehole field or your trench field as a storage and basically divert that extra heat.
Yeah, you would be using the field as a heat dump. And that's all in the design of this system, whether it's residential or commercial. That's, you have to consider, there's a bit to consider when you do this. There's a lot of manuals and books on this, and a lot of information.
Yeah.
Just to bring it up right now, it's the International Ground Source Heat Pump Association that's recently moved from Oklahoma State, where it started about 3 decades ago, to a nonprofit organization because the college wanted to kind of relinquish responsibility. But they have a lot of information available on all aspects of ground source heat pump design, latest technologies, interfacing, solar, and not only solar is one aspect of heat, which obviously we're mentioning today, but there's other sources that are both renewable and non-renewable that can be used. So we're the renewable source, which is similar to the ground source heat that's being extracted from the ground. That's why we're pairing it with the ground source heat pumps. Again, a lot of them, if you need more education, there's through that association, also through a couple of other people that supply components to ground source heat pump systems. One is Calefi. There's others, Balgosset, I believe. There's other companies out there, but Calefi has a lot of information on not only a pretty good series on heat pumps. Mm-hmm. One of the interesting things that came up, and kind of why solar is we're pushing this or asking you to look at it, is some of the systems out there, they have their ground source loops. They work well at the beginning of the heating season, but as the season, if it drags on, you may start to see a drop. It's kind of like the battery's getting low, and you're not getting as much heat as you need. Just you've pulled it all out. Mm-hmm. So the best thing with heat pump systems, there's again a lot of design, is to use it. Don't overuse it. Don't have an 80-degree house. Keep the heat moderate to your comfort level, and if necessary, solar may be able to provide that extra heat you need to get through the winter. This is happening in colder climates, Wisconsin, Minnesota. It's just they're pulling more than they have available. So solar can interface to kind of keep that system. And it's not, the nice thing about it doesn't have to be high temperatures. That's the thing. A little bit higher, 10 degrees, if you can put 10 degrees into the system, the heat pump will take that heat and put it in and raise it like it's doing with the loop, with the ground source loop, and provide adequate temperature. There's also new designs for all the people that do radiant floor or radiators, emitters we call them, if they're above the floor, to maximize the heat extraction at lower temperatures. So a lot of them use forced air little fans, computer fans, on top of the baseboard heaters, and they get 4 times, 5 times the output doing that. So these newer emitters that are coming out and are out now, and then designs in the floor, if you have a radiant floor, concrete floor with the tubes, designing them to max. What you want to have is lower overall temperatures. That maximizes your efficiency. So you want to boost the temperature a little bit going into the heat pump and lower the temperature through the emitters and through the floors. Lower temperature translates to more heat being pushed into the floor, into the living space, into the conditioned space. So those two items, it's a balancing act, and there's a lot of software design available for that from manufacturers of the tubing and from the heat pump manufacturers. Use all those resources. They're very, very helpful in moving through the ground source heat pump realm and also solar. For us, we have information on how much energy we can supply, what temperatures you need. There's a lot of variations that can happen, and it's all specific to the project you're working on.
Exactly, as Bob was mentioning. So there is that keeping the earth temperature at the optimum level, because there is that seasonal. So we have to realize a lot of time these systems were designed several years ago. Now the climate is rapidly changing. We're seeing harsher winter. A lot of time you need more heat than originally anticipated to keep your house at the comfortable level that you wanted, or that building, whatever it might be. And there's another factor. So you might actually run out of heat for the season. That's one thing. And then over time, you have to realize with the geothermal heat pump, you're extracting the heat from the air during the coldest month of the year. So not only you're taking out the heat, but also the environment is taking out the heat constantly. So it's like having too many plugs connected into one battery, one of those USB batteries. If you have like 10 phones charging at the same time, it will just deplete really fast. So what happens with that over time is also, now there are some research, some anecdotal evidence, some research showing that in 10, 15 years, the average ground temperature fall below the optimum temperature for the heat pump to be able to operate optimally, basically. So adding that solar loop will allow what we call pre-charging or supercharging or whatever we want to call it of that geothermal loop in the summer, in addition to provide some domestic water, hot water that you need, or some other heating application that you might need, assisting it during the winter time, then supercharging it in the summertime, keeping it at the temperature level that the system can operate at year round. And there are, as Bob was saying, there are so many different designs, so many conceptual designs, so many actual deployed designs that work amazingly well. And there are definitely, if anybody wants more information, please, I think between me and Bob, we spend hours and hours on this research, so we have a healthy amount of at least resources to share. So anybody wants more information, please just send us an email and we will just forward everything that we've gathered to you. Another thing that could be very beneficial is by adding, because so the number of boreholes, or the length and the depth of the trenches that you need, is basically calculated by how much BTU you can take out of the ground per square foot, or per square or per basically feet depth that you're going in, whatever it is. You calculate that number, and basically the geothermal heat pump manufacturer or installer will tell you that, okay, you need this many boreholes at this depth, or you need this many feet of trenches at this depth to be able to extract that much heat. So what if you can bring in a certain amount of BTU, let's say 40,000 BTU per day, from a solar thermal collector, and then you have 10 of those, 15 of those, whatever number that you have, you now have this additional amount of BTU that can offset the number of boreholes and the amount of trenching that you need to come up with, the BTU required to keep that property at temperature when we need it. So that's another advantage of basically, and when these sophisticated design softwares are used, they take all this into account and come up with the sizing of the solar thermal and the geothermal that is optimum for that application. So a couple of points of comparison between solar assisted ground source heat pump versus just the regular source ground source heat pump. It has a better COP, obviously, compared to just a simple ground source heat pump or a electric resistance for that matter. It has a lower electrical consumption than both those systems because, again, a heat pump is a compressor. It's always more energy intensive to run a compressor to run a, hypothetically speaking, same size circulating pump to basically transfer the same energy. So if you have a solar assisted ground source heat pump or geothermal heat pump, there are times that you're running a circulating pump to gather that energy instead of a compressor. So obviously your electric consumption will be lower compared to a system that constantly have to run a compressor to generate that energy. The potential obviously for COP saving is much higher, and we'll see a great payback period depending on the location of the system, anything between 8.3 years to 23 years. Keeping in mind that the life expectancy of a solar thermal water heating system is 25 plus years, 20 plus years. Those are very, very promising number for combining these technologies together.
Right. The bottom line is that the little higher temperature going to the heat pump brings up the COP, and that's the COP is coming, the energy is coming from solar, which has a solar thermal, which has a high COP off initially. So that's where we're seeing the savings and the efficiencies and just bringing that water temperature up, not much. Sometimes, again, that design, there's people that, heat gigantic fields and water pools and all kinds of methods to provide that heat over the heating season.
Mm-hmm.
So it doesn't have to be 130 degrees, it can be 100 or 90. The average temperature on a ground source in the ground is 70, maybe less, 60, 50 degrees. So, that's pretty low. If you can bump it 10 or 20, you're doing very well. It's all in the design, what your goal is with the system in the home.
Yeah. So basically, this is one of the possible, basically integration methods for solar thermal collectors and a ground, as they call it, ground collectors in this diagram, the ground source heat pump. So basically, they both feed a buffer tank, Amir another, and then the buffer tank is feeding a heating system that goes to radiant panels. And
right, that's one design.
Yeah, that's one possible design. Just
possible.
And then
the buffer tank is just an expansion of that. The buffer tank's needed. That just keeps everything. It's like a battery in your car. It keeps everything running. So it's not, if you're operating off the alternator, the voltages are going every which way. The battery makes that smooth. It's like an expansion tank in a water system. It just keeps it running smoothly. There's no spikes.
Yeah.
And you could have like the solar collectors, if you wanted to expand that could have its own storage system that feeds the buffer. So there's a lot of possibilities. It's, again, all has to start at the design phase and with the owner and the architect and the engineer and the heat pump people. A lot of people get involved in this, but that's how it comes out properly.
Absolutely. And I think as we see more and more of these systems, then we'll probably see a mainstream of designs coming up that are not considered by the trade professionals, by the industry professionals as the most efficient design, as the most cost-effective designs. But we need to see more and more of these systems. And I think the way the energy trends are going, the way we're seeing where we're heading, I think we will eventually see that. Um, this is another possibility of combining these systems. I basically borrowed the line diagram from Gaylord Olson, and I want to thank him right now, actually, now that we have his diagram up, for his help with me preparing for these seminar or the webinar that we're having. And it's been a great resource, and he has a lot of knowledge, a lot of interesting designs, and several patents when it comes to geothermal systems. And if anybody is interested in knowing more about his system and his designs, please reach out to me, and I'll be more than glad to share his contact information with you. But again, in this design, we basically have two loops underground, and his suggestion is the two loops will be placed at different depth. So one is much lower, one is at a higher depth in the ground, allowing them to be used as basically both cold and hot storages. And basically, depending on the time of the year, you will be able to, at the same time that you're using one of the loops for your heat pump, you can use the solar thermal to precondition the second loop to be used later on during the winter time. And then you can also basically use the cold loop to potentially cool your house during the.
Right. Yeah, a lot of cooling. Radiant cooling is developing rapidly. One of the major designs is in the ceiling, radiant cooling and heating in the ceiling. But the cooling allows for a minimization of dew forming. Mm-hmm. Like if you had it on the floor and you're cooling the floor, you could get a wet floor if you get dew point. So the moisture would come out on the floor and you slip on your floor. So having it on the ceiling eliminates a lot of those issues when you try to cool with liquid.
And also, expanding a little about the loops that we have here, I talked about at the beginning of the slide about the two ground loops, but keep in mind, these doesn't have necessarily be ground loops. So you can have one ground loop, and then one of the loops can, for instance, be a air source.
Right.
So you can have, for example, let's say for radiant dispensing units that just dispenses heat to generate the differential that you need to create cold during the hotter months of the year.
Or the heat pumps, they have combination systems, heat cool. They even have them forced air, multi-function systems that have forced air aspects to them, so you can have cooler air blowing, or if you want warmer air blowing. So if you don't have a full radiant system, then you can have part of the home having forced air. So again, a lot of options out there.
Oh yeah,
and choose from. Sometimes it gets daunting, but a lot of them are done. They're working well. Mm-hmm. People are very happy.
So I think this is basically the gist of the slide is the multi-source. Right. That's the message, right? In order to kind of address that big elephant that we talked about at the beginning, we never look at our technology, the solar thermal technology, as basically the silver bullet that's going to solve all our problems. No, we believe it's a great technology. It has a wide range of application that it can be used, but all these different technologies, all these different high efficiency methods that were developed has to come together in order to be able to really address this energy question that we have now to replace all these loads that were addressed with fossil fuels for so long, and we had access to it for so long, and it was relatively cheap to use for so long that you're just so used to designing and having the systems like that now it's difficult to think about more complex systems. But
before before we started digging in the earth for our fossil fuels, we burned fire, wood, and
Coal.
that caused, coal they dug.
They dug, yeah.
Yeah,
Right.
that's even,
Surface level.
And you could see, I mean, deforestation occur quite rapidly in the whole history of the use of wood and deforestation, and how, going back to the Romans, they had ships. That's all they did was go and
bring the wood.
Bring wood back for the Roman Empire. So, and we see that's what we see on overtly, outwardly. Now we're seeing, things being pulled out of the ground, but their result is CO2 and atmospheric changes and climate changes, which we'd like to kind of slow down and reverse.
Mm-hmm.
So it's kind of where this is all,
and also
energy costs and availability. So just need to get a handle on it. We're working as fast as we can, but we also want it to work.
And dependency, Bob, you have to keep in mind that you cannot pull that stuff out of ground everywhere. There are certain places on Earth that have access to that stuff in their grounds, and they, whether we like it or not, they control it. So no matter what, we're going to be dependent. So if you're not generating your energy locally, if you are counting on someone else to provide that energy, then you have your own set of problems. And if you don't believe me, you can just check with European leaders right now, and I think they can give you a complete story of what's happening. But there are several great examples as these technologies are developing and they're being deployed, and trends been going on for some times, and that's great because we have case studies that go back several years, and we can see that the systems were in action and actually did work very well. This is a large scale and by far the largest project of its kind in the nation, and it's the Ball State University in Indiana, and it has a district geothermal heating system. I believe close to 4,000 boreholes provide heating to 47 buildings, and geothermal coal to 47 buildings and heat to 20 buildings in the campus. Again, large scale system. You can see the overall cost of the system is $70 million, which is a big price tag, and it was definitely higher than the price of the coal burning, state-of-the-art coal burning boiler. But here is the problem that I have whenever people compare the cost of such and such boiler to the cost of a geothermal system or a solar thermal system in my area of work. And that's my question. When you buy a boiler, they're not selling you the fuel that you will be using for the next 20 years. It's not part of that price tag. You're not paying for it, obviously, but you will be paying for it on a monthly basis as soon as you install and start running that boiler. With a geothermal system, with a solar thermal system, with the air source heat pump system, you still have an energy bill attached to it. That's your cost of electricity to run that system. And then that's when that COP really comes to effect. But with a solar thermal system, with a COP of 20, you're paying very, very little for running that system and not a cent in fuel. Until somebody figures out how to privatize Sun, we don't have to be concerned about that. So your fuel is free for the basically conceivable life expectancy of the system, which is 20 plus years. So that's something to definitely take into account. And then we can see that the system ends up saving them $2 million a year just on basically the energy saving that generated. This is a very interesting project. Drake Landing Solar Community in Alberta, Canada, use geothermal, solar thermal to provide heat to an entire district, subdivision of housing. The houses were basically 30% more efficient than your average R2000 houses in Canada. And in these systems, basically combining the geothermal and solar thermal, large solar thermal field, we saw that a reduction of approximately 5 tons of greenhouse gases per year.
Per house.
Per house, yes, per home. That's the key number there. The system were able to fulfill more than 90% of each home's space heating, definitely 100% of the domestic water heating load, I believe, on these systems. And we saw a COP of above 30. So these systems are no longer being monitored. They stopped monitoring the systems after 10 years of monitoring them. So I think they stopped back in 2018. And the houses were built in 2008, if I'm not mistaken. And then for 10 years, they monitored the system, and the result was published. So 4 years ago, basically, as part of the published result, it was deemed that that these type of construction is not very cost effective. And of course, because again, we go back to cheap natural gas. If it's available, this is not justified. But I think we all had basically this is the third round of the rude awakening that we have with fossil fuels, that they can go up in prices all of a sudden and without any prior notices. We experienced the entire energy crisis in the 70s and early 80s, and now basically it's the same situation, but this time it's not only financial. We have a better understanding and more clear sight of what's in front of us as far as the dangers of climate change and what we have to do to eliminate or basically to reduce the amount of greenhouse gases that we're releasing to the atmosphere. So now the mathematics and numbers have changed for these systems, and something that might have been deemed not cost effective a couple of years ago, it might very well be very cost effective now. And the projects that used to take 10, 15 years to see a return of investment are now seeing a much higher return of investment, basically rate, and then reduced duration of return of investment for like 7, 8 years now from 10, 15 years. So we're seeing the trends changing. Definitely the direction of greenhouse gas reduction is going to continue toward that basically goal of going toward net zero as much as possible and as fast as possible. And I think, if generally speaking, there might be periods of time that the cost of fossil fuel might come down, but I think the general trend will be an upward trend for fossil fuel going forward.
6, 7, 8 billion, how many we are on the planet, they want a piece of the action too. So there's only so many places you can get oil at the moment.
Yeah.
And relatively, the cost is can go up and down. So if we can move as quickly as we can, but again, in my opinion, these things have to work. So it goes back to design, goes back to the equipment that and the project, and building these houses more energy efficient so you can make the systems don't have to be quite as large. And then eventually we'll move, to maybe you have a little heater on your wall that's there just in case things need to be boosted, but most of the time it just sits there. It's a little. Most of these, from the information I have, ground source heat pump systems, and also just geothermal heat or heat pump systems may have a secondary heater there. Just they do it. Engineers don't, and I agree. Architects, they don't want to have someone calling with a cold house, so they'll put it in. It's ready, but it's never used.
So it's a redundancy, right?
It's there in case you need it. Engine, you don't want to get a call in the middle of winter and you're sitting by your fireplace if you're an engineer or architect that your client is cold.
Exactly.
And because they ran out of, everything just like Texas 2 years ago, all heck broke loose when the cold weather came through. So we can't be ready for everything, but an engineer can put something in, and an architect to say they covered all their bases, and as long as the boiler has either natural gas or electricity or some other fuel, propane, to provide that little extra when the climate and local weather gets really nasty, then he's okay, and so is the homeowner.
So we're gonna do a quick Q&A. I'm sorry we went a little longer than anticipated. We only have a few minutes left until 12. But if anybody has any additional questions that we don't get to, just please feel free to email us. I'm just gonna skip over the Q&A slide and put our contact information. That's my email address and Bob's email address or phone numbers. If you have any question, shoot us an email, give us a phone call. We'll be more than glad to talk about solar thermal. Then when it comes to geothermal, we don't know a whole lot, but we can definitely put you in touch with people who do know a lot about these systems and design and stuff.
That's not our forte on the specifics. Mm-hmm. The integration is fairly straightforward, but all the fields and the boreholes and all that is all specialty. Usually the people that have been doing it know what they're doing. Manufacturers usually right there to help, both with the tubing and the equipment, the actual heat pumps that are working in, and then the emitters, the heat sources are out there too.
All right. So any questions for us? Let's see. Let's look at the chat. Okay, let's see. Geo-optimized for ground loop design. You have to burn the dust off your electric. Hot and okay. Let me just. I'm just reviewing all the comments.